Okay, I will post the solutions in Moodle. Some of you did very well. It was fair, right? Some of you made a very minor mistake. So okay, to continue from where we left. If you have any question about your grade or anything, you can let me know. So let's look at section 2.8, and this is the subspaces of Rn. So we looked at what we meant by Rn. So we said it can be R2, can be R3. So these are the number of terms there. 3 terms, 2, 3, 4, like that. So n for n spaces, n spaces. Okay, so the first section that we're looking at is subspaces of the vector space. Subspaces of the vector space. Okay, let's define what we mean by the subspace. So definition 1.1. Okay, so what is a subspace? So we can say a subspace of Rn is a subset H of Rn So a subspace of Rn is a subset of H of Rn, such that the zero vector is an element of H. The zero vector is an element of H. And U plus V, the vector U plus V, is also an element of H. And C, and then you multiply by U, is also an element of H, where U and V are elements of H, and C is a constant, which is an element of real number. So zero vector is an element of the subset, which is H. So subset is actually a small part of the set. So you can have the whole set, and then you take a small part of it. You call that one a subset. So a subset, you can call that one H. So that H has the same properties with the whole set. So the small set has the same properties like the whole set. Okay, let's look at example number 1. Example number 1. A. Rn, the real number, which is the whole set. The whole set is a subset or subspace of Rn. So the whole space can be the subspace of the whole space. So we can get this one. So the proof is just the same as the one from the definition, 1.1. So 1.1. Number B, zero vector is also a subspace of Rn, where 0 is a zero vector in Rn. Zero vector in Rn. So we have the two of them. We have the whole set, and then we also have the zero vector. So both of them are the subspaces. So we can prove these. So let's prove. So we have zero vector to be the element of the zero set. Okay. Then if we let the U and the V to be the elements of zero vector, the U and V to be the elements of zero vector, and C to be the element of real number, then U is equals to zero vector and V is also equals to zero vector. U is equals to zero vector. Therefore, then U plus V is equals to zero vector plus zero vector, which is the same as zero vector. Is equals to zero vector. So then also U multiplied by the constant C is the same as C multiplied by zero vector, which is equals to zero vector. So then is a subspace of Rn. Subspace of Rn. So remark. Let's look at the remark. So we can say we call zero vector and Rn the trivial subspaces of Rn. The trivial subspaces of Rn. Example number 2. Example number 2 is H, which is equals to x1, x2, element of R2, whereby x1 plus x2 equals to 1, a subspace of Rn of, in this case, R2 is a subspace of R2. So what do we need to know? So So the proof or the solution. So we know that the zero vector of R2 is 0, which is equals to 0, 0, right? The zero vector of R2 is 0. So then, since x1 equals to 0 and x2 equals to 0, then x1 plus x2 is equals to 1. So therefore, 0 is not equals to 1. So 0 is not equals to 1 because x1 and x2 are zeros. So 0 there is not equals to 1. Therefore, that is not. So it is not a subspace of R2. So H is not a subspace of R2. So H is not a subspace of R2. Let's look at theorem 1.2. Theorem. A subset H of Rn is a subspace if and only if zero vector is an element of H and C1 U1 plus C2 U2 is also an element of H for any C1 C2 element of real number and U1 U2 element of H. U1, U2. So actually this theorem here is just similar to the definition up there. So the only difference is that we have introduced the constants, which are C1, C2 in H. So C1, C2 in H. So we can prove this simply. So we can briefly prove this one. So since this one is if and only if, then you need to prove the forward and the backward direction. So for the forward direction, then you can say for any C1, C2, which are elements of R, of real number, and U1, U2, and these are elements of H. So we have C1, U1 to be the element of H, and C2, U2 to be also elements of H. Then, and C1, U1 plus C2, U2 is also element of H. So if one of them is an element of H and the other one is an element of H, then when you add all of them, then they are also in H. They are also in H. Backward direction. So for U and V to be elements of H, U and V to be the element of H. So we are going now back. Then, and also C is an element of real number. Then U plus V equals to 1 U plus actually 1 V. And also these are elements of H. So they're in H. So 1 and 1 are the constant. Then, and CU is actually similar to CU plus 0, 0 vector. And these are also in H. These are also in H. Therefore, H is a subspace. H is a subspace. Okay, let's look at another theorem, 1.3 theorem. The span V1, V2, all the way to Vn is a subspace of Rn. Is a subspace of Rn. Where V1, V2, all the way to Vp. We can say this one is Vp. Elements of Rn. Elements of Rn. So the span is also the subspace of Rn. So we can prove. So let's prove. Now, if we write, if we remember, we wrote the span of V1, V2, all the way to Vp to be equals to, let's say C1 V1 plus C2 V2 plus CP Vp, whereby C1, C2, CP elements of real number. So that is what we did last time. So the span is actually the linear combination. So that is a linear combination. So then the 0, so we have the 0 vector of this now. So the 0 vector here will be equals to 0 V1 plus 0 V2 plus 0 Vp. And this is in what? In H. So we can see that the 0 vector is in H. Because all those will give us 0. So then, if we let C1 and C2 to be elements of the real number. We let C1 and C2 to be elements of real number. And U1, U2 to be elements of H, to be in H. Then to find X1, X2, let's say XP, Y1, Y2 to YP to be the elements of real number, such that U1 to be equals to X1 V1 plus X P VP, and U2 to be equals to Y1 V1 plus YP VP. That's right. Then u plus v is equals to, you add this, so x1 v1 plus x2 v2 plus xp vp plus y1 v1 plus y2 v2 plus yp vp. All these are vectors. All those are vectors. Then when we collect the like terms, then what we get here is, we put this one C1 here and C2 there, C1 and C2 there. So when we multiply this one by C1 and also this one by C2 here, then if we open the brackets, then it is C1 x1 v1 plus C1 x2 v2 plus C1 xp vp plus C2 y1 v1 plus C2 y2 v2 plus Cn or C2 yp vp. Okay. Then when you now you can actually factor out v here, so C1 x1 and then v1 plus C1 x2 v2 plus C1 xp vp plus C2 y1 v1 plus C2 y2 v2 plus C2 plus, if you continue like that, C2 yp and then vp there. Then when you now collect the like terms and then you factor out v1 in each one of them, so what you get is C1 x1 plus C2 y1 v1 plus C1 x2 plus C2 y2 v2 plus, if you continue like that, plus C1 xp, yeah, plus C2 yp and then vp. So we realize that all these are now the elements of what? The elements of H. So they are actually in H. So as you can see, this is now the linear combination. So therefore, you can say that. So our H is a subspace of Rn. H is a subspace of Rn. Okay, let's look at another example. Example number 3. Example number 3. Determine whether h, which is equals to, put it here, h, which is equals to x1 minus x3, x2 plus x3 minus 1, x1 minus x2 minus 1, element of R3 such that x1, x2, x3 element of real number is a subspace of R3. Determine whether that H is a subspace of R3. It's a subspace of R3. So then what you can see here is that, let's look at the solution. So what we need to do is we need to determine whether the zero vector is equals to 0, 0, 0 is in H, or the following linear system is consistent. So we need to determine whether the zero vector 0, 0, 0 is actually in H, or we write this one in linear system form, whereby x1 minus x3 equals to 0. X2, in this case, x2 plus x3 equals to 1. And then x1 minus x2 is equals to 1. It's equals to 1. So we can equate this one to 0, 0 each. So we need to check whether this linear system is consistent or not. So if it is consistent, then it is a subspace of H. So we write this one in augmented matrix form. In this case, what we get is 1, 0, negative 1, and then we put our 0 there. 0, 1, 1, and then 1. And then the last one there is 1, negative 1, and then 0 and 1 there. So when we reduce this, so once we reduce, then we need to reduce the last one. So we can say the new R3 is R3 minus R1. So what we get is 1, 0, negative 1, 0, 0, 1, 1, 1, and then 0, negative 1, 1, and then 1. Then we reduce this. So to get the new R3, then R3 plus R2. So what we get is 1, 0, negative 1, 0, 0, 1, 1, 1, and then 0, 0, 2, and then 2. 2, and then 2. So we can see that we have the pivot positions in each one of them. So, and the last row here is not contradictory, right? So the last row here is not contradictory. So it shows that that linear system is consistent. So then the solution of this is we now reduce this completely. So to reduce this one completely to get the values of x1, x2, and x3, then we need to make this and this one to be zeros. So this and this to be zeros, since this one is a pivot. So first of all, you need to reduce this one to 1 and 1. So the new R3 will now be 1/2 multiplied by R3. So we get to 1, 0, -1, 0, 0, 1, 1, 1, 0, 0, 1, 1. And then finally, we make all these to be zeros. So to get the new R1, then it is R1 plus R3. To get the new R2, then it is R2 minus R3. R2 minus R3. So finally, what you should get is 1, 0, 0, 1, 0, 1, 0, 0, and then 0, 0, 1, and 1. So our solution here, which we could have actually gotten from here, is actually x1 is now equals to 1, x2 is equals to 0, and x3 is equals to 1. X3 is equals to 1. X3 is equals to 1. So we don't have the free variables there. We only have the basic variables. Only have the basic variables. Now, if we now set y1 to be equals to, bring this one here, y1 to be equals to x1 minus 1, y2 to be equals to x2, and y3 to be equals to x3 minus 1. Equals to x3 minus 1. Now, if we let y1 equals to, bring this one here, equals to x1 plus 1, y equals to x2, and y3 x3 minus 1. Then if we go and replace this in this equation here, in this h here, if we bring this into this h here, where there is x1, x2 like that, then so what we're gonna get, so our new x1 here, so x1 here will be y1 plus 1. This will remain like that, and then x3 is equals to y3 plus 1. So when we come and replace all this to the solution up here, so then our h will now be equals to x1. So our x1 is y1 plus 1, and then minus x3. x3 is y3 plus 1. Yeah, and then our x2 there is now y2 plus our x3 is y3 plus 1, and then minus 1, and then x1 is y1 plus 1 minus x2 is y2, and then minus 1 for all y1, y2, y3 elements of real number. Then if we simplify this, then what we get is y1 minus y3, y2 plus y3, and y1 minus y2. y1 minus y2 for all y1, y2, y3 elements of real number.
So for that, so the middle one, right there, where this is y2 plus parentheses y3 plus 1 minus 1, over 2, right? Okay. How can they can can you just get rid of the -1 right there?
Okay, so y1, so 1 minus, so that will be y1.
What about the next term?
Oh, the next one, yeah. Yep, the next one is oh, there is a, yes, there is a minus here. So the next one is y2 plus y3, right? 1 minus 1. You see?
Okay.
Yep, 1 minus 1 there, and then like that. So then, in this case, what we get is now equals to. So what we get is now equals to. So if we write this as a linear combination, then it is actually the same as y1. In this case, there is 1 here. There is no y1 here, so there is a 0 there. And then there is y1 here, which is 1. And then plus y2, you get y2 here is 0. Y2 here is 1. And then y2 here is minus 1. And then plus y3. Y3 is minus 1 there. Y3 here is 1. And then y3 here is 0. Whereby y1, y2 elements of real number. So then, then we can see that our H now is a span of these vectors, which is 1, 0, 1, 0, 1, and minus 1, and -1, 1, and 0. -1, 1, and 0. So those are now the span of. So using the definition that we did up there, the theorem, then therefore, if the span, the 3 of them, so we have 1, 3 vectors here. So therefore, since these are 3 vectors, that is now spanning R3. So therefore, this is an element of R3, since we have 3 vectors. So it spans R3. So it means that this H is now spanning R3. Okay, let's look at the next section, which is number 2, the column and the null space. The column, the null space says of a matrix. The column and the null spaces of the matrix. Okay, let's start from the first one, which is the column space. And this is the definition. So what is a column space? So the column space of an M by N matrix, let's say A, which we usually write this as call of A, a column space of an M by N matrix, which is A, which we write as column A, is a subspace of Rm, which is spanned by the columns of A, which is spanned by the columns of A. Rm, which is spanned by the columns of A, if A is equals to, if A is equals to A1, A2, An, then the column of A is equals to the span of A1, A2, all the way to An, such that A1, X1, or we actually start from A1, X1, A1 plus X2, X2, A2 plus Xn, An, such that X1, X2, Xn are elements of real number. And this is also equals to Ax, such that X is an element of Rn. Ax. So that X is an element of Rn. So the column space is actually the span of the vectors A1, A2, and An. So we will see that once we reduce this matrix A, once we reduce the matrix, the columns which will give us the pivot positions are the ones which are spanning A, and those are what we call the column space of A. The column space of A. So, for example number 4. Example number 4. Determine whether B is in column space of A, where our A is equals to -3, -2, 0, 0, 2, -6, and 6, 3, 3, and our B equals to 1, 14, and -9. 1, 14, and -9. So determine whether B is in column space of A. So what do you do here? So what you need to do is you need to check whether when we reduce the augmented matrix, then the solution that we get should be consistent. So if it is consistent, then actually this B is spanning or spans this. So actually that B will be in column space of A. So we write this, so the solution, we reduce this matrix, which is the augmented matrix, -3, -2, 0, 0, 2, -6, 6, 3, 3, and then here 1, 14, and -9. So once we reduce this matrix, you go home and reduce that matrix. So what you get is -3, -2, 0, and 1, 0, 1, -3, 7, and then 0, 0, 0, and 0. So that is what you will get. So that is what you will get. Now, since the last row here is 0, 0, 0, so it is not contradictory, right? So then it means that since Ax equals to B is consistent, since that is consistent, then our B is in the column space of A. is in the column space. So once you go and reduce this, so as long as this is not contradicted, then it is consistent. So it means this B spans this vector. Okay, now let's look at the next one, which is the null space. So what is the null space? So 2.2 definition. So the null space of an M by N matrix A, which we write this written as null space of A, NULA, is the set of all solutions of the homogeneous matrix equation AX equals to 0. AX equals to 0. i.e., the null space of A equals to X, which is an element of Rn, such that AX equals to 0. AX equals to 0. So that is the null space. So the null space is actually now getting the solution of the homogeneous linear system. So it means you need to reduce that matrix completely to get a solution of x1, x2, and then x3. So that solution there is the solution that you get is now the null space of A. So it spans, so it's the null space of A. So let's look at the theorem on this here. If A is an M by N matrix, then null space of A is a subspace of Rn. Null space of A is the subspace of Rn. So the column space of A, we say is the what? The subspace of what? Rm, right? So for this, the null space is the subspace of Rn. For the other one is the subspace of Rm. So this is the subspace of Rn. Okay, so we will meet on Wednesday.
Correct. I think it's City's investigating.
Exam, I was just doing, it should have been an 8.
Okay, we. So it's, yeah.